Hello, y'all, and welcome to lesson 89 of my DP chemistry curriculum. Today we're going over reactivity 2.2, or sorry, 2.3.2 and 2.3.3. The first section, we're going to be talking about how equilibrium law describes how the equilibrium constant K can be determined from the stoichiometry of a reaction. We'll be able to use the equilibrium constant expression, form an equation of a homogeneous reaction. The second section, we'll talk about the magnitude of the equilibrium constant, how that indicates the extent of a reaction at equilibrium, and it is temperature dependent. We'll determine the relationship between K values for reactions that are the reverse of each other, as well as if they're at the same temperature. We'll include what happens at each K value, being less than one, far less than one, equal to one, greater than one, and far greater than one. With all that said, let's talk about equilibrium a little bit. So generally we consider the extent of a reaction. So consider extent of reaction as how far right it goes. And what that means is right is to the products. Because when we look at an equation, the right side is the products. It's always reactants to products. So our extent of a reaction is how far to the right it goes. If a reaction leads to the products, then we would say the equilibrium is shifted to the left. Products equilibrium is shifted to the right. Now, we actually can quantify the extent of reaction, and we quantify that with the equilibrium constant. That is Kc. It is also sometimes referred to as just K. We generally use K to represent equilibrium constants. You'll notice we use K to represent almost every constant, but generally Kc will specifically be equilibrium, with K kind of in general representing some type of constant. This is not the same K as in the rate reaction, though, I will say that. Now, the equilibrium constant Kc is specifically a ratio that represents the concentration of reactants and the concentration of products at equilibrium. We can also say that it describes the equilibrium mixture, which once again is that mixture of reactants and products at equilibrium. So the equilibrium constant is going to describe these ratios, and so we have naturally an equation for it. With that, we'll consider a generic reaction, AA plus BB reacts to form an equilibrium, CC plus DD. And those lowercase, those are the coefficients of balanced equation. So in this reaction, A and B react to form C and D at various coefficients. The equilibrium constant Kc is just a measure of the concentration of our products raised to their own exponent, or raised to their own coefficients as exponents, divided by the concentration of the reactants, also raised to their coefficient as an exponent. And so this is how we describe that ratio. It is essentially the amount of products divided by the amount of reactants. If we have more products, we can expect Kc to be higher. If we have more reactants, we can expect Kc to be lower. This value will not be negative. The value will always be at minimum zero, or it will not hit exactly zero, but it will approach zero, and it can be incredibly high as well. So if we are to do this in example, if we were to determine the equilibrium constant for something such as the Haber process, we can look at nitrogen gas plus 3 hydrogen gas reacts to form 2 ammonia gas. And Kc for this reaction will, of course, just be the concentration of ammonia at equilibrium raised to the second power divided by the concentration of nitrogen raised to 1 times the concentration of hydrogen raised to the third power. That is our equation for Kc. So now that we have the equation, let's explore what it actually happens when we put this into practice and what the equilibrium constant can describe us. So why don't we try with a given concentration? So given concentrations at equilibrium, we can determine magnitude of our equilibrium constant. So we'll still use the Haber process just because we already have that one written out. And we'll assume that our nitrogen gas concentration is 0.80. Our hydrogen gas concentration should be triple that according to our coefficients if we started with exactly perfect stoichiometric amounts. And our ammonia concentration in this case, we might say is 0.40. This is just some random example. This does not have to be every example of the Haber process. But in this example, at equilibrium for a given temperature, as this is very temperature dependent, we will find that Kc is equal to 0.40 raised to the 2 second power divided by 0.80 times 2.40 raised to the third power, which gives us a value of 0.014. In this case, we find that this value is less than 1. Our Kc is less than 1. The value is small. What this indicates is that we have more reactants. We know that's true already because we can see right here that we have more reactants in total than products. But you can tell that our equilibrium concentration shows that when we plug it into our equilibrium constant equation, that if the number on the bottom is larger than the number on top, our value will be less than 1. So we have more reactants. We could also say the reaction favors reactants. Another way we could say this is that the equilibrium favors the left. We may even say the equilibrium is shifted left. So towards our reactants. Our equilibrium mixture is favoring the reactants. So the really big thing to understand about our equilibrium constant is that it just describes our products over reactants. And because it shows our products over the reactants, we can create kind of a mathematical representation of it, where we say that a Kc that is very, very much less than 1, like something like 10 to the minus 5th, 10 to the minus 6th, this would be almost entirely reactants. So if we're looking at a reactant mixture, it's almost entirely reactants. A Kc that is just less than 1, like kind of what we see with this Haber process example, is that it is mostly reactants. For a Kc that is equal to 1, it's similar amounts, or what we would say is appreciable. I have no idea how to spell it. Appreciable amounts of each reactants and products. For Kc greater than 1, it is mostly products. and for Kc far greater than 1, it is almost entirely products. The last thing to go over before we finish off equilibrium constant and we just start using it in our general day-to-day about equilibrium is talk about the equilibrium for reverse reactions. So we have our Haber process that we've used 8 million times, and you know it now by heart. I'm not going to put the state symbols, just save a little time. So that is our forward reaction. The reverse reaction can just be written as, 2NH3 reacts to form or decomposes to form nitrogen gas plus 3 hydrogen gas. This is our reverse. You may notice that in our reverse reaction, the Kc for the reverse is now N2 H2 divided by NH3, and that will be raised to the second power. What you may notice is if we kind of lock this in our brain for a moment and go back to where we first tried it, it's the inverse. So we can actually relate our Kc reverse is equal to Kc forward raised to the -1 power. So the reverse reaction and the forward reaction just have inverse equilibrium constants. And we can just find that by continuously re-deriving our equilibrium constant equation. So I hope this helps you understand the equilibrium constant, its magnitude, and what that means, and have a great day.